All right, welcome back everybody. Here we are in section 9.8 of AP Calculus BC, finding the area of a polar region, or the area bounded by a single polar curve. It says here in my intro, area problems work differently in polar coordinates than they do in Cartesian coordinates. Instead of talking about finding the area under curves, we're going to be looking for the area bounded or enclosed by curves. And we're going to be finding these areas by creating circular sector regions emanating out from the origin of the polar plane. So take a look to the right here. To find the area enclosed by the curve r equals f of theta, from theta equals alpha to theta equals beta, shown to the right, the formula that we're going to use is area is going to be equal to the integral from alpha to beta of 1/2 r squared d theta. Okay, now you might be sitting here going, well, where on earth did that formula come from? And honestly, it just comes from the area for from the formula for the area of a sector of a circle. Because what we're going to do is we're going to take, at each of these values, we are going to take, a very narrow band that kind of looks like this. I guess I should make it a little wider so we can see what's going on. Something that looks like this. And we're going to slice this region up into all kinds of circular sectors like this one. And if you remember, to find the area of the sector of a circle, we find that by taking, and I've broken it all down for you here, the area of the sector of a circle, we find by taking the area of the circle, which is pi r squared, and then we multiply that by the portion of the circle that the sector occupies, which, since there are 2 pi radians in the entire circle, if we take the angle, which is what portion of the circle we're talking about, and divide it by the angle that represents the entirety of the circle, this gives us the portion of the circle that we're looking at here. And so when we multiply all that together, gives us this formula 1/2 r squared theta, which looks a whole lot like what we see up here. The only difference here is, instead of this being r squared theta, it's r squared d theta, and the reason why is because we're subdividing this up into infinitely narrow circular sectors, and so the angle down here is a small increment of theta. It's the change in theta instead of this actual angle that we use in the sector formula. And then we go from one end of the region to the other, and that gives us the area inside of that curve. There's one other important thing we need to consider when we're doing these problems, and that is where the endpoints, the limits of integration, are going to be for us. We need to pay attention and be aware of where the curve's going to start and where the curve's going to stop for our area finding purposes. Okay. Now, historically, the majority of these questions on the AP exam have been calculator active questions, which makes it easier for us to find those limits of integration. Or frequently they might give us a picture of the curve or give us the intersection points of the curve. But I don't think you're going to see very often where you've got to come up with the curve by hand and figure out where the region starts and stops based on looking at this by hand. I just don't think you're going to see that very often on your AP exam. So let's go ahead and we will analyze the curve r equals 3 sine of theta and look at how we're going to find the area inside of that curve. All right, so r equals 3 sine of theta. And I'm going to set this up. I always set these up so that they are path when I graph them, the line with the circle on the end, so that I know whether the curve's getting retraced, because I've got it set up right now with the theta max at 6 pi. I'm going to go ahead and change that to 2 pi. And we'll make this, make our theta step pi over 36. And since the radius is 3 here, I know that this curve shouldn't be more than 3 units in any direction. So I'm going to make my graph from -4 to 4 so that I can see the whole thing. Now, it doesn't really matter if I see a perfectly accurate graph here. I'm okay with distortion, but what I do notice when I graph this, we'll regraph it again, notice how we graph the curve, and we're watching that path go, and it retraces the curve again. So that means that 0 and 2 pi are not my limits of integration here. I'm going to have to figure out what my limits of integration are. So I'm going to go ahead and trace the curve, and when theta is 0, it starts down here. And I'm going to go around and see when I get back to that position. And the angle when I get back to that position is pi. And so our limits of integration are going to be from 0 to pi, because those are the angles that are forming this region. Okay, now realize what's going on here as this angle goes around the curve. Like here we are at, well, let me go back. Let me go backwards so I'm in the interval that we're talking about. So like, let's go to here. There's pi over 6. So like from pi over 6 to pi over 4, this cursor moves along the boundary of this curve. And what happens is we're tracing a region that comes from the origin over to this curve. And as the curve moves along, it's gradually building like a circular sector there, like I showed you in this drawing here. You know, it's starting at this point here, and as the angle moves around the curve, it sweeps out this area up until where it stops. And that's how that works for us there. So to trace the whole curve, it went from 0 to pi. So we're going to go ahead and set up our integral. This is going to be from 0 to pi. I've got 1/2, as a constant out in front, r squared times d theta. And there's the integral expression that I'm going to use to find the area inside of the curve r equals 3 sine of theta. And so now I'm going to go ahead, since we're usually going to do this on our calculator, I'm going to go ahead and do it on my calculator here. And as long as I can get my calculator on my screen, there we go. Go out to my main screen, and I'm going to have 1/2 times the integral of the quantity 3 sine of theta, quantity squared, with respect to theta, from 0 to pi. If you have your calculator in polar mode, if you're using like an 83 or 84, that, you know, xt theta n button should automatically bring theta onto your screen when you do this stuff. And now I'm going to go ahead and calculate. Here we go. 7.069. 7.068, also acceptable. And that is our area bounded by this curve. All right, let's go on to the next example. Example 2. Find the area of the inner loop. Inner loop? What? The inner loop of r equals 2 plus 4 cosine of theta. I feel like we really need to look at this graph because it says something about an inner loop, and I have no idea what that even means right now. So let's go ahead. By the way, I'm kidding. I know what that means, but maybe you don't know what that means right now. Let's go ahead and graph this. R equals 2 plus 4 cosine of theta. I know that the maximum value of 4 cosine of theta is 4. So I'm going to set my window up. 2 plus 4 is 6. So I'm going to set my window up to run from -6 to 6 here. And make my graph. And we make the graph, and when we make the graph, now we see, oh, that's what they mean by the inner loop. This loop right here, the area of this loop right here. Okay, so as far as my curve goes, this entire thing is bounded by the curve 2 plus 4 cosine of theta, so that's going to be my r value. So I can set up my integral a while. This is going to be 1/2 times 2 plus 4 cosine of theta, quantity squared, d theta. And now all I have to do is find my limits of integration. And in order to do that, I'm going to go ahead and trace this curve. It starts out here at 0. I want to find the angle where the inner loop starts. It looks like that's at 2.094. If you don't recognize that, that's about 2/3. Looks like it's about 2/3 of pi, because pi is 3 and change. This is 2 and change. I can verify that pretty quickly. Go out to my main screen, type in 2 pi over 3, and I see that that indeed is 2 pi over 3. So that's going to be my lower limit of integration. And then my upper limit of integration, I'm going to continue tracing around the curve. And now you see how I'm moving along the inner loop, and I'm sweeping out the area. As this cursor goes around this loop, I'm sweeping out the area from the origin, the pole, inside of that loop, and I go all the way to 4.1887, which is double what I had before. That's going to be 4 pi over 3. And so I'll now have my area formula set up. And let's go ahead and calculate that area inside of the inner loop. Using our graphing calculator, we've got 1/2 times the integral of the quantity 2 plus 4 cosine of theta, quantity squared, with respect to theta, from 2 pi over 3. I'm always going to use the exact values if I know them. You know, maybe you looked at that and you didn't recognize that that was 2 pi over 3, and so you just took all the decimal values from your calculator and used that as your limit of integration. That's fine. I'm going to tend to try and use exact values, at least when I recognize them. And I'm going to go ahead and hit enter now, and let my calculator calculate a little bit, and hopefully it will give me the area inside of that inner loop. It's taking a while. My calculator is slow and lethargic. There it is, 2.174. And that is the area of the inner loop of that curve. Okay, we're going to call it quits here for today. Well, not for today, for this video. And we're going to come back in video number 2, and we'll look at examples number 3 and 4 from this lesson at that point in time. All right, have a good rest of your day, everybody. See you next time, and enjoy yourself. Bye-bye.